Ladies and gentlemen, welcome to the second part of my lecture on problems with statistical tests in empirical work. Last time we have been discussing hypothesis testing. You might remember, we had this simple single equation model where we have a dependent variable denoted as yt, and we have predictive variables or regressors denoted as x1t, x2t, and x3t. Whereas ut measures the error term of the regression model. So, and as an example, if we are in marketing environment and we might have a model where we want to investigate the impact of different marketing actions. We said yesterday that x1t could be the changes in expenditures with respect to marketing action 1, and x2 could measure, for instance, the changes in expenditures with respect to marketing action number 2, and so on. And obviously then our yt would be in this context the changes in company profits. So this is a very general model, and we also argued that we could expand this model. We could account for more variables and so on and so forth, but we have to ensure that we have all relevant variables here in our model. So we finished last lecture with a simple hypothesis test. This is what we typically are interested in empirical research. We want to investigate, we want to test hypotheses. Let's say we want to investigate if our marketing action 2, measured by variable x2t, if it's significant, if it has a significant impact or a positive impact on our profits of the company. So we are interested in beta 2. We want to investigate if beta 2 is statistically significant. So as a null hypothesis in this case, H0 would be then that our beta 2 is equal to 0. So under the null hypothesis, we always assume that there is no effect, because we want to reject the null hypothesis, so that we know that if we make an error, our significance level is the maximum error. It's the type 1 error. You might remember this from statistics classes. So under the alternative hypothesis H1, beta 2 is unequal to 0. And if we reject the null hypothesis, which means in turn that we accept the alternative hypothesis, so this would mean that our variable x2 has a significant impact on our company profits. So how would we do that? So we finished yesterday our lecture by computing the t-statistic for this test. So if this is our pair of hypotheses, it's a single test of a single parameter, so we can use the t-test. This is what we usually do in statistics, and our test statistic lambda follows a t-statistic. This is what it means. So we have to compound lambda, and we talked about it yesterday. How do we do that? So we have our Ols regression. We perform our Ols regression. We define our input matrix, the regressor matrix. We define our vector. What we get is then we run a simple regression. We know our parameter vector beta hat is then given by x transpose x inverted times x transpose y. So in this case, our parameter vector beta hat is then simply given by the alpha hat as the first increment of that vector. The second component is the beta 1. The third component is the beta 2 hat. And the last component is the beta 3 hat. Now we have to put a hat on that because that's an estimate. So what we do is we grab the second point estimator from that vector. beta hat 2, and we divide it by this square root of the corresponding variance. Yeah? Very simple. So that's our test statistic. Yeah, that's our lambda. What we do then is we compare this number here with the normal distribution, because according to our assumptions, if our assumptions are true, then this test statistic, lambda, now it's lambda hat, because it's estimate, our estimated test statistic follows under the null hypothesis a normal distribution. So this is what comes out, and now we have to compare this value that we computed with the critical values of the standard normal distribution. So we compare this value with 1.96 and or minus 1.96. So obviously, if it's below minus 1.96, then the impact would be negative. So we assume, or what we are interested in, if this impact is negative, if its impact is positive. So if our marketing action actually makes sense. If we should continue to have expenditures for this marketing action. So we compare this value here with 1.96, and we would like to see that it's basically higher than 1.96. So in case this is our lambda hat is higher or larger than 1.96, then we would conclude that this point estimator beta hat 2 is statistically significant given a 5% significance level, because we know that we have here obviously in this area 2.5% of the probability, and here also 2.5% of the probability, which makes 5% of the overall probability. And obviously, given we want to have a 5% significance level, we use these values here, and given that this point estimator is in this critical zone here, then we would reject the null hypothesis. And the error that we do is our significance level, is the maximum error is 5%. So we have control about the error that we do in case the null hypothesis is actually right. We have this type 1 error, obviously, you might remember that from basic statistics classes, and this is always the significance level. But on a 5% significance level, we are quite sure that whenever this t statistic is in this critical zone, then we would reject the null hypothesis. So this is what we would do in case we are interested in testing a single parameter. But the question arises, how do we proceed if we have a combined hypothesis? If you would like to test, we would like to test the marketing action 2 and 3 at the same time. How do we proceed then? So in case we would like to test a combined hypothesis, let's say that beta 2 equal to 0 and beta 3 equal to 0, against the alternative hypothesis that either beta 2 is equal to 0 or beta 3 is equal to 0. So it's enough, we would reject the null hypothesis if only one of these guys would be statistically significant. This is what it means basically. Again, we have our recall that this is our equation, that where we basically implement our test upon, and obviously the test statistic lambda looks now quite different. So in this case, this is a very general equation on the very general test, which is called the Walt test. It's called the Walt test. And the test statistic follows a chi-square distribution. So, and here is what it looks like. So we have obviously here a term on the left-hand side. We have a matrix R. We multiply a matrix R with the parameter vector, with the estimated parameter vector beta hat minus a small r. We transpose this term, and we multiply it with again with the matrix product. We multiply the matrix R, capital R, with the covariance matrix of our point estimator beta hat times R transposed. And this term here in the middle is then inverted. And then we multiply it again with capital R times beta hat minus R. It's the same part that we have here in the front, but here it is transposed. Yeah? So that's a very general test statistic, which you really should be aware of. Yeah? And so in our case, the question is now, okay, we know that the point estimator beta hat, we know already how it looks like. We have this alpha hat here is the first component, then we have our beta hat 1, beta hat 2, and beta hat 3. That's our beta hat point estimator. And now we know, okay, what is small r? Yeah? It's obviously a vector. Yeah? And in our case, because we have two parameters that we would like to test, then this parameter vector here, this small r, that is here and here in this lambda, that is obviously then a 2 by 1 vector. Yeah? If we have three parameters that we would like to test at the same time, then this would be a 3 by 1 vector. So let's say we have L is 2, restrictions. Yeah? In this case, our R is then an L by 1 vector. Yeah? It has the same dimension that we have restrictions to test. Furthermore, what do we need moreover? So let's put this one here. Maybe we should put this one here. So our small r is a simple 2 by 1 vector, or a L by 1 vector. And what we would also need, obviously, here in order to compound this test statistic, we would like to know what is R, this capital R. So capital R, obviously this capital R depicts us the corresponding components that we would like to test from our parameter vector. Yeah? We know that our parameter vector is 4 by 1, or in order to make it more general, it's k by 1. Yeah? This is k, the number of parameters that we have here. So it depicts us for each of these restrictions that we would like to test, the corresponding parameter out of this vector. So obviously the first one is beta 2, and it's the third parameter here, right? It's the third parameter, alpha, beta 1, beta 2. So it's 0, 0, 1, 0. So if we multiply this guy here with this vector here, it gives us obviously beta hat 2, which is the first component that we would like to test here. So what else do we need? We are interested in the third beta. Beta 3 should be 0, and that is the fourth parameter here, right? So it's the fourth parameter, 1, 2, 3, and this gets a 1. So that's our R, capital R. It gives us the corresponding parameter out of this vector. Yeah? Now we get this guy here. So this is how it looks like. So R is then obviously a 2 by 4 matrix, and in more general, that's a K. If this is K, and this is our L, our R is therefore a L by K matrix. Yeah? And obviously, we cannot have more restrictions than we have parameters. So obviously, L is smaller or equal to K. Yeah? This is what always needs to be true. So okay, now we know our R. Yeah? We know what is our small r, our capital R. This is a matrix, that's a vector. And depending obviously here on the restrictions that we want to test. So if we want to test if beta 2 is 1, or if beta 2 is, let's say, 0.5, beta 3 is 0, then we will put in here 0.5 and 0. So all of this, we can directly put it from our hypothesis that we'd like to test and put it into our vectors or into our matrix. Yeah? So very simple. But yeah, now we know everything basically. We know also what our covariance matrix is, beta hat. Yeah, we know that already. It's sigma square times x transpose x inverted. Yeah? That's the covariance of our point estimator beta hat. Yeah? So that's basically all we need to know. And now we can just plug it into this formula here, and then we get our corresponding test statistic. Yeah? We need some space here. Let's take this away. As I told you yesterday, you have to make your notes here in my course. So the corresponding test statistic, lambda, the estimated test statistic lambda, follows under the null hypothesis a chi-square distribution with 2 degrees of freedom, or more specifically it's L. It depends on the restrictions. We have 2 restrictions here that we would like to test. Therefore, our test statistic is distributed as chi-square with 2 degrees of freedom. If we have 3 restrictions here, then obviously we would have a chi-square distribution with 3 degrees of freedom. So, and obviously the test statistic looks pretty much different. So the chi-square distribution has a probability distribution which looks like this. It has a longer tail on the right-hand side, and the critical value for the chi-square distribution with 2 degrees of freedom is 5.992. So if our test statistic, we run this test statistic and we get a number here out of it. So if this value here would be larger than 5.992, if it would fall into this area here, which is the critical area. So if you would have a lambda of, let's say, 7, then obviously we would reject the null hypothesis, which means that our point estimators B2 and B3 are simultaneously significant on a 5% level. Again, this is the corresponding value here for 5% probability here on the right tail of the distribution. So whenever this estimated test statistic falls into this critical area here, then given the 5% significance level, which we typically apply in empirical research, we would reject the null hypothesis, which means in turn these are jointly significant, which means in turn that our marketing actions 2 and 3 simultaneously or jointly have an impact on the changes in profitability here of our company. This is basically how we would conclude. And now the question arises, so what is lambda actually? So if you would basically multiply it out, if you would multiply out this formula here, how would it look like? What is it actually? So you can do this at home, the derivation. It's actually pretty simple, but what comes out is lambda. If you multiply this out, if you multiply R with our estimated beta hat, so what it gives us, I told you already that it depicts us the corresponding component of that vector beta hat that we're interested in to test. So if you multiply this out and subtract a vector of zeros, so what comes out is simply, and we have to transpose it obviously, so what comes out is beta hat 2 and beta hat 3. This is what we get out of here. That's this. If we multiply out this term in the middle, what you will see is when you make your homework that what comes out is we have here the variance. It depicts us the variance from our beta hat 2. We have here the covariance of beta hat 2 and beta hat 3. We have here the second element on the main diagonal is the variance. If this operation here gives us then here the variance of beta hat 3. And here we have obviously then, because the covariance matrix is symmetric as we know, here we have then the covariance of beta 3 hat and beta 2 hat. Yeah? So obviously this in the middle here, this operation, it depicts us the corresponding variances and covariances of the covariance matrix from our beta hat estimator. Yeah? And if we have obviously two parameters here, we have to take into account obviously also the covariance between these two parameters in our test statistic. Yeah? And here, the term here, we know already what it is. It's this guy here transposed. So it's beta hat 2 and beta hat 3. So that's a 1 by 2 vector, right? That's a 2 by 2 matrix. Because this guy is inverted then, as you see here, that's a 2 by 2 matrix. And what we have here is a 2 by 1 vector. So obviously, lambda is a scalar, it's a number, obviously. So this is what comes out. And now you see the difference between a chi-square test or Walt test and the t-statistic. So obviously the difference is that once we have a joint hypothesis or combined hypothesis, we have to take into account the covariances between these parameters. Yeah? So that's the main difference. So what we can also do is we can implement this Walt test if we want to test only one parameter. Yeah? So that's also possible. And that's the beauty of these test statistic. It's a very general and it can be used in many different circumstances. Yeah? So let's say we would like to test if beta hat or beta 2 is equal to 0 versus beta 2 is unequal to 0. So how would this R look like? So our R in this case would look like, it would be just a vector. Our capital R would just be a vector, and it would have obviously 0 in the first place, 0 in the second place, and a 1, because that's the guy we are interested in, this beta 2, a 1 in the third place, and then also a 0 in the last place. It would be then a 1 by 4 vector. Our R, our small r, this guy here, what should it be? It should be 0. So our small r is then just a number. It's 0. It's 1 by 1. It's 1 by 1 matrix. So obviously in mathematics you would define small r as element. M stands for matrix, and here's the dimension. It's 1 by 1. So it's very straightforward. So, and obviously, what's the reference distribution? So it's a chi-square distribution. How many degrees of freedom? 1. L is 1, because we have only one restriction that you would like to test. So again, this chi-square distribution with 1 degree of freedom, it's the same thing. It looks a little bit like this. It has a longer tail on the right-hand side. And we know from statistics classes that chi-square distribution is a squared, normally distributed random variable. So that's basically what it is. And the corresponding critical value is, in this case, 3.84. We know that above 3.84, if we have the chi-square distribution with 1 degree of freedom, chi-square distribution with 1 degree of freedom, we know that above the value of 3.84, we have 5% of the probability. So we would, and this is obviously not coincidence, so we know from the normal distribution, the critical value is 1.96 and minus 1.96. So if we square 1.96, what comes out is 3.84. So that's why, again, the chi-square distribution with 1 degree of freedom is the normal distribution squared, basically. So obviously we have to compare then our test statistic lambda hat, what comes out here. We have to run this test. We know the increments already, we just have to plug it in. We run our test and we compare the estimated test statistic lambda hat with the chi-square distribution with 1 degree of freedom. We check if we exceed the critical value of 3.84. If we do, we reject the null hypothesis, given a 5% significance level. Which means then, in turn, again, that our point estimator, or that our marketing action 2 has a significant impact on the output here. The only difference is here, in this case, we can only test, obviously, if it's significant or not. Obviously, it could also be minus 1.90. The critical value, it could be negative. The point estimator could be negative as well, significantly negative. This is what we do not know if we implement this test here. Of course, we know it, implicitly, because we know what are the numbers of our point estimators here. So of course, if this number is negative and our chi-square test gives us that it's significant, then we know it's significantly negative, right? So that's actually not the problem anyways. So you see that our Walt test, based upon the chi-square distribution, is very general. It's a very important test that is often used, and you can use this test also if we have a multiple equation model. So that's basically the beauty of this test. It's a very general test, and it has been subject to massive investigations in statistics. Important test, and we will use this test in what follows regularly, and we will basically see or investigate what happens if we deviate from our core assumptions. So now the last thing that we have to discuss here is, okay, so obviously we need, let's take this away. We need some more space here. So in the derivation, or when we implement our test statistics, we always need the covariance matrix, obviously, of our beta hat. So we know if our assumptions are true, then the covariance of our beta hat is then given by sigma square, which is the residual variance times the regressor matrix transposed times itself inverted. So this is true if our assumptions hold. But what's that guy? How can we estimate the residual variance? So this is very simple. So we know we have our data vector y, we have our data matrix x. We know we have to run. The first thing that we do is we get our point estimator beta hat by x transposed x, inverted x transposed y. Then we know, obviously, that our y is equal to x times beta plus u, which is our residual vector. And what we also know is, if we have estimated this guy here, y minus our regressor matrix x times beta hat, we can just bring this term here on the left-hand side of the equation, is then equal with our estimated residual vector. So we get our estimated residual vector by simply subtracting the regressor matrix times our estimated parameter vector that we have estimated already here in this step, from our data vector y. Very simple. It's a very simple operation. So we know that our u hat is a t by 1 vector. So, and how do we estimate now our sigma squared? So I told you it's the residual variance. So we can estimate it as sigma hat squared, yeah, it's now estimated, so it's sigma squared hat is an estimate, and this is simply given by we have 1 over the number of observations, which is capital T, minus our 4 regressors. Here we have 3 x regressors, and here obviously also one vector of ones. Yeah, you might remember that. So we have then here 4. It's then t minus 4, or in more general t minus k. Yeah, but obviously in the limit, if t is very large, this doesn't matter. Yeah, so times u hat prime times u hat. Yeah. So u hat prime is 1 by t times t by 1 is 1 by 1. So that's a number. And we divide this number by the observations t minus k. Yeah? That's the residual, the estimated residual variance. Yeah? That's also very important, because this guy we need to have an estimate for that guy in order to be able to compound the covariance matrix of our point estimator beta hat. So now we have everything, and now we can implement every test. Yeah? And this is also what we will do later on using computer software. Now we have to remember that given that this is our model, the covariance matrix of our point estimator beta hat is given by this expression here. Yeah? So we can only simplify this expression so that it becomes sigma square times x transpose x inverted. Yeah? This is only true if our error process, if our ut is identically and independently distributed as normal with 0 mean and sigma square variance. Yeah? So only if this assumption is true, yeah, we can, you might remember the operation that we could do here with this term in the middle. We could simplify this as sigma squared times the identity matrix, grab this out of the parentheses and so on and so forth, simplify this expression by sigma squared times x transpose x inverted. But again, this is only possible if our error terms are normally distributed and independently distributed, but just obviously a consequence of that. So what it means is we have an error process t, and here is our u hat t. So the error process, if we plot it against time, it should look well behaving. It should circulate around 0, and it should be a well behaving process. So, but what could happen? What could happen instead? So let's say we have estimated a model, and we plot our residuals. This is now the first case that we would like to discuss here, and we have here 3 different scenarios. We plot in each of these scenarios here for the first case. We plot our estimated residuals of our model against time. And what you see here are a lot of bumps, bulges. It doesn't look like here, like we would like it to be. So what could it be? What's the problem here? What's the problem? So the problem is that our error term, it looks like as if it behaves like a random walk, which is evident through these bulges here. It moves around. Obviously, it's around 0, so it's basically the average, the sample average of our u hat t is 0 in all of these cases here. But obviously we see bulges and bumps, which is an indication that this is obviously not a process how we would like it to have. So the question arises, if we have this problem here, what impact does it have on our covariance matrix of our beta hat? Yeah? This is what we would like to discuss now. So let's discuss the random walk problem. Yeah? So let's assume first that we have an innovation process ET, and this ET is independently, let's just take this away, it's independently and identically distributed as normal with mean 0 and sigma square variance. Yeah? So this is a well-behaving process. Yeah? For all t is from 1 until capital T. Okay? So let's assume that our error ut is given by a sum from I is 1 until t, that our ut is given by a sum from I is 1 until t, yeah, so it's the same index here, of this error, yeah, which is well behaving. Yeah. So what's the expectation? What's the expectation of our ut? So what we have to do is we have to plug in this guy here. So it's the sum from I is 1 until t of our ei. Yeah. So what's that? So let's just write it down. So it's basically it's I1 plus I2 plus I3 plus and so on until IT. Yeah? This is what it comes out when we write it down, what it is. And now we know that the expectation operator is a linear operator, so we can move this operator herein, yeah, to each of these random variables. Yeah? And what we know is that the expectation of our ET is 0 for all of them. So obviously the expectation of UT is then 0. So obviously that's not the problem. Yeah? So the expectation of our UT is not the problem. What about the variance then? Let's have a look at the variance. So what's the variance? Sigma square. The variance is defined, sigma square is the variance, or sigma square u, sigma square u, and this is sigma square e. Okay, so it's the variance of our ut. And how is this defined? So it's the expectation of our ut minus the expectation of our ut squared. Right? And we know already that the expectation of our ut, that's 0. Yeah? We know that from our previous analysis. So what remains is the expectation of our ut squared. Now we have to plug in what it is. So it's obviously this guy here. So it's the expectation of the sum from I is 1 to t from our ei. And this expression is squared. Right? So if we add t is equal to 1, the expectation of this guy here, it's simply the expectation of our ei, so it's then e1, right? It's only e1 squared. And what's that? Well, that's our variance of our ei, right? So that's sigma squared e. So what if we are in t is equal to 2? Now the variance of our ut is given by the expectation of E1 plus E2 squared, right? What is that? So let's solve this. It's E1 squared plus 2 times E1 times E2 plus E2 squared. Right? Now we have just solved this formula here. So again, the expectation operator is a linear operator, so we can move it in the parentheses. So what's the expectation of E1 squared? So again, that's the variance, right? That's the variance of our random variable E. What's the second guy? What's the expectation of 2 times E1 times E2? Well, that's the covariance, yeah, of E1 and E2, and that's 0, yeah, because that's a white noise process. It's identically and independently distributed. Because it's independently distributed, yeah, the covariance here is 0. So what remains is then, obviously, 2 times the variance of our random variable sigma square of our random variable E, which is sigma square E. And if we now go to t is equal to 3, yeah, you can do this at home. So what you will see is the variance of our ut is then 3 times sigma square E. Yeah. So it increases, so the variance is obviously a function of time. It's dependent on the time. So if t goes to infinity, it follows that the variance of our ut is infinite. And just for you at home, you can do this at home. So now we have done the operation for the variance. So for the covariance, yeah, let's write it here. So the covariance between ut and ut minus k is equal with t minus k times the variance sigma square E. Yeah. But this is obviously for our purpose not so important, but you can, of course, you can do this at home as your homework. Yeah. It's important to show here, yeah, that the variance of our ut, yeah, if t goes to infinity, yeah, the variance is infinite. So what does that mean for the covariance matrix of our beta hat? So let's take this away. So it means for the covariance matrix of our beta hat estimator, yeah, that this guy here, sigma square times x transpose x inverted, because our sigma square is infinite, so our covariance matrix is not defined. We cannot estimate the covariance matrix of our beta hat. So that is obviously a serious problem, yeah? And even though that we get an estimate, yeah, for our sigma squared, yeah, for the residual variance, in sample everything is finite. Yeah? In sample we get always an estimate for something, but we have shown here that the theoretical variance doesn't exist. So that means that the variance is sample specific. Yeah? It means everything is sample specific. Yeah, we cannot make statistical inference, if we know that the variance doesn't exist. That's basically a very important thing to have in mind. If the variance doesn't exist, or if the variance is infinite, our covariance matrix is sample specific, and we cannot draw any conclusions based upon our parameter estimates. That's it. So now the question arises, what's the problem with our model? We have to bear in mind how our model looks like. This is our model here. We have yt as a dependent variable, and we have here our regressors. So what could be the problem here? So what we have to do is, we have to check. For instance, we have to check first our dependent variable yt, and we have to do the same for all the others as well. So what we have to do is we have to check if this guy here is a random walk. We have to check all of our variables in our system here if they are random walks. So, and we do this using the so-called Diggy-Fuller test. Diggy-Fuller test. So this is only one out of many tests. It's a unit root test. Okay, it's a very old test, but it's still used. And this is one of the tests that you usually also encounter in econometrics. And this is only, as I said, there are many different tests, and this is just one out of many. So what we have to do is, in order to implement this test, the test is based upon the unit root null hypothesis. Okay, so we have here our model yt, on yt minus 1 plus epsilon t. So that's our error term of our model, our regression equation. So we can add now on two sides of this equation the lag variable. So yt minus 1 is equal with alpha times yt minus 1 minus yt minus 1 plus the error term epsilon t. So we have just added on both sides. We have expanded the equation with a lagged value of the yt variable. So this is in essence delta yt. And what we have here is then a phi yt minus 1. And here again we have our error term et. So, and what's this phi? Well, that's nothing else but alpha minus 1. Obviously, it's alpha minus 1 times yt minus 1. So now we have our model. So under the null hypothesis, we assume that our variable is a random walk. So we test if our phi is equal to 0. And that's the random walk hypothesis. Under the alternative hypothesis, H1, our phi is smaller than 0. And in this case here, yt is stationary. As it should be. So now we have to remember that if we do this test, so we can implement this test very easily. We know that we have our data vector, y1, y2, y3, and so on and so forth until y capital T. So what we simply have to do is here, we have to subtract each value from the previous one. So we create a new vector, that has one observation less. Obviously, it's a capital T minus 1 by 1 vector. So we have the first element is then y2 minus y1. The second element is then obviously y3, minus y2. The third element is then y4 minus y3, and so on and so forth. The last element is then yt minus yt minus 1. Yeah, so that's very simple transformation. So we can do this for all of the other vectors as well, yeah, and then run the same test. So that's very simple. That's very easy to do. So, and what does that actually mean? Yeah, let's say alpha is 0.5. So if our alpha is 0.5, that means this is the same thing as if our phi would be minus 1.5, right? So it's because of the similarity here. If alpha is 0.5, yeah, then our alpha would be, our phi would be minus 1.5. If our alpha is 1, phi would be 0. So what does that mean? So obviously it means if our alpha is 0.5 and significant 0.5, so it means that our yt is stationary, right? If our alpha is 1, it means that our yt is a random walk, because then we would have this equation here. Yt is yt minus 1 plus this error term. Yeah. In this case here, here's a 1, that's a random walk. Yt is a random walk. Yeah. If yt is 0.5 times yt minus 1 plus an error term, then it's stationary series. So these two time series here look very different, obviously. Now the first one here looks as earlier as our residual term earlier. It has bumps. Whereas the second process here will look like this. It's more well behaving. Yeah? So that's the purpose with the Diggy-Fuller test. Yeah? And let's take this away now, because we need some more space here. So we have to, after we implemented this test, yeah, we have to check the t-statistic of our phi, yeah, in difference form. So we estimate the model under the alternative hypothesis. Yeah, so we take the difference series and regress it on the non-difference series, yeah, t minus 1. So it's pretty simple to estimate this. So what we have to do is then we have to compare the t-statistic of this phi with different critical values. Yeah? It's not normally distributed. Yeah? Diggy and Fuller, they have basically run these simulation studies and they figured out the critical values. So we have to compare this with the 1% critical value is minus 2.66. The 5% critical value is minus 1.95, and the 10% critical value of that distribution under the null hypothesis is minus 1.62. Yeah? And this is based upon, it is obviously dependent on the number of observations, if we have more than 250 observations in the sample. Yeah? So we compare the t-statistic again of phi. If it's below, if let's say phi is the t-statistic of phi is, let's say, minus 3.5, minus 3.5 is lower than minus 1.95. So in this case, we would infer that our time series, yeah, that our yt is stationary. Yeah? So then obviously we don't have a problem. Yeah? But if the estimated test statistic would be, let's say, it's minus 1.5. Yeah? Minus 1.5 is higher than minus 1.95. It's even higher than minus 1.96. So on any level here, our time series yt would be a random walk. Yeah? It would be a random walk. So in this case, we would be supposed to operate with the difference time series. So what we have to do is the solution is obviously that we implement our model not in levels with level variables, but in difference form. Yeah? So we would basically run the model on delta yt. Yeah? So we would obviously not, if our basic model would be, our independent, or of our dependent variable yt would be the profit of the company, and we would run our test, and the test would show, okay, the profit obviously is a random walk. We know we cannot run our model because our covariance matrix for the point estimator is not defined. So what we have to do is, okay, we have to operate with the changes in profits, given that our models, if our model suggests, okay, our yt is a random walk. So we have to operate with the difference. We know we have to operate with the difference time series here for the yt variable, and this means then in practical terms we do not use the profit of the company, but the changes in profits. So the same thing we have to do also for the x variables, because obviously we do not know beforehand which of the variables behaves like a random walk and which of the variables does not. So we have to implement this ADF test, or this Diggy test, for all of these variables. So that's important to bear in mind. And moreover, let's take this away. So it's also important to know that this is obviously, there are many different versions of this Diggy test. So that's basically the plain version, the simple Diggy test, but in practice you operate usually with the augmented Diggy test, which is called the ADF test. Augmented Diggy test. Remember now that we talked about the omitted variable problem. So we have to always to make sure that our error term in our regression equation is well behaving. And in order to ensure that this guy is well behaving, what people do in practice, when they implement the test regression for the for getting the phi, what they do is usually they add some lags here. Some, let's say from I is 1 until k, capital K, or actually we have used already k for denoting the number of regressors. Let's call it h, okay? And then we have here y delta y t minus I, plus our error term epsilon t. So, and this means if h is, for instance, let's say h is 2, then this term here is simply delta y t minus 1 plus delta y t minus 2. And then we have obviously here also a point estimator, so we have here then a delta, let's say have here delta 1 and here a delta 2. So we add basically lags of our difference series that we have here on the left hand side, in order to ensure that we have, that this guy here is really, that there's no dependency structure left basically, so that this guy here is really behaving as an IID process, as a well-behaving process. So, and obviously the length of lags of lagged left-hand side variables here on the right-hand side, that's obviously an empirical question. Yeah, and as we already said, it's better to have too many variables here than have too little because of this omitted variable problem. Yeah? So, and moreover, we can then, obviously, if we have here, first, if we start with a lag order of 5, if our age is 5, and we see when we run the test that the last 3 lags have insignificant point estimators, we can then obviously run an F-test or a chi-square test, a Walt test, and check if they are jointly significant. If not, we can just neglect them and implement the model with only 2 lags here. And if all of them are insignificant, obviously, then we do not need the ADF test, and we can just go with the standard Diggy-Fuller test. Yeah, that's basically how we would do. And what we hope, is if our Diggy-Fuller tests or our augmented Diggy-Fuller test suggests that let's say we run this test for all variables here, for our x3, x2, x1, and our y-t variable, and it suggests that all of these guys are random walks, and we implement what we would do is we would implement the whole model here in differenced. So we would have here delta yt is equal with alpha plus beta 1 times delta x1t plus beta 2 times delta x2t, and so on and so forth. And what we would hope for then, obviously, is that our error term ut, once we implement the model in difference form, that this guy is then well behaving. This is basically why we would do that, and hope that this guy is now not anymore, doesn't have these bumps, these bulges anymore, but that we go from that to a well-behaving error term, so that we can compound the covariance matrix of our point estimator. Let's consider another case. Now we have case number 2. Let's say we have estimated our model. Again, we use the same model here for our example, and let's say that we plot the residuals against time, our estimated residuals u hat t, and this is what comes out. This is how it looks like. So we have a period, where obviously where there's a very low variation in our residuals. Then we have a period where the variation of our residuals is very high. Then again, we have a period of very low residual variation, and then again a period of very high residual variation. So we talked about that already in the introduction to the lecture series. So this is called volatility clustering. So what would happen? So how is this possible, or how can we model this kind of process? So let's assume, we have an innovation process that is identically and independently distributed as normal with 0 mean and standard deviation of 1. So our innovation process now is again assumed to be like well behaving. We have the Gaussian bell curve here, 0 mean and standard deviation of 1. So that's our E or epsilon t. So let's assume that our residual term, our regression error ut is a function of that normally distributed innovation process, like we have here. Ut is equal with sigma t times epsilon t. So what's sigma t? So let's say sigma t squared is a function of a0 plus a1 times ut minus 1 squared. So our sigma t squared is a function of our squared residual process, lagged. And a0 and a1, these are parameters, obviously. So this is called, if you study the literature, So this is called an arch process. It's the simplest form of an arch process. It's an arch 1 process. Yeah? Autoregressive, R stands for autoregressive and CH stands for conditional heteroscedasticity. Autoregressive conditional heteroscedasticity of order 1. Order 1 means we have here one lag. So that means that the variance at time t is dependent on one lagged squared residual or error. If we have an arch2 model, obviously, then we would have two lags here. We would add here an alpha 2 times ut minus 2 squared. An arch3 process, the same. You can just expand on that. So that's an arch process. We have now here, obviously, the simplest form, just for illustration purpose. So what's the expectation? Now we operate with the conditional expectation. You see, unlike earlier, now we have the expectation at time t. So what's the expectation, conditional on time t, of our residual term ut? So we can write into the expectation operator what it is. It's defined as sigma t times epsilon t. So it's the expectation at time t from sigma t times epsilon t. So, and why can we do this operation here? So obviously what we have done here is we have moved the expectation operator conditional on time t in the parentheses here. Why can we do that? And we have moved out the sigma square, or the sigma t in front of the expectation operator. Why is it possible? Well, it's possible because at time t, and that's why we use the conditional expectation here, because at time t, we know that the sigma t, respectively sigma t squared, is dependent on lagged residual squared. So, and this information, t minus 1, we know already at time t. So it's nothing new. It's not random. We know that because this is not random at given time t. We can move it outside the expectation operator. What remains is in the expectation operator at time t, epsilon t, and we know that epsilon t is distributed with 0 mean. So the expectation of epsilon t is 0. Because the expectation of epsilon t given time t is 0, the whole expression here becomes 0. That means that the expectation at time t from ut is 0. And what that means that our beta hat, our OLS point estimator, is unbiased. You remember, this was a very important property. This result means, okay, our beta hat is unbiased. So what about the variance then? What's the variance of our ut? We have seen in the previous case, obviously the variance was infinite. Because the variance was infinite, we didn't have a covariance matrix here, okay? We didn't have it, we couldn't compute it anymore. So that was a big problem, right? So that's why we were supposed to operate with difference series. So what's going on here now? Okay, what's the variance at time t? Again, we operate with conditional variances here, in order to see the statistical properties here. The variance at time t from ut, what is it? Well, it's the expectation at time t from what? It's ut minus the expectation from ut squared. That's the standard formula for the variance operator. So we know already from the previous step that the expectation of our ut is 0. So that means that this expression here simplifies to the expectation at time t from what? From our ut squared. So we just have to square the first random component here. So what's that? Well, we can just plug in what it is. We know that our ut is a function of epsilon t times sigma t, and sigma t is, again, it's just depending on past information. So we can plug it in here for our ut and square it. So again, we have to square, obviously, what we have to do, we have to square both components here, so sigma t to the power of 2, which is sigma t squared, and epsilon t to the power of 2, epsilon t squared. And again, because sigma t, the information, conditional on time t, this is known, everything is known, it's on past, the random component here is based upon past information at time t minus 1, and that's known at time t, so we can move this guy here outside the expectation operator squared. This is what happens here. What remains is the conditional expectation at time t from epsilon t squared. And we know that epsilon t squared, what's that? That's the variance of epsilon t, and we know that the variance is 1. So what remains is that the variance conditional at time t from ut is sigma t squared. It's exactly what we have here. So again, what we see here is obviously that the variance is depending on time t. So it's unequal, it's not constant, it's not sigma square. Sigma square is now depending on time t. Moreover, what one can show is that the covariance at time t, the conditional covariance of ut and ut minus 1 is 0. This is your homework. This is what you should do at home, using the same logic that we have used for compounding or computing the conditional variance. We can do the similar operation in order to show that the conditional covariance at time t, ut or ut minus 1 is 0. But the tricky part here is obviously that's not the problem here. The covariance is not the problem. That's exactly how it should be. This is not the problem either here. That's also all right, but that's the problem. The problem is obviously that the variance is time dependent. So it's not constant as we would like it to have. So, and this obviously is reflected also here in the, we can see it actually from the graph already. If we plot the residual of our model, we can see that there is something strange going on. So what's now the impact of this on the covariance matrix of our point estimator beta hat? And this is what we would like to discuss now. So once again, according to our assumptions, what we had earlier is that we could simplify this guy here as sigma square the identity matrix. And what followed is that the whole expression here simplified to sigma squared x transposed x inverted, as our estimated, or as our covariance matrix of our point estimator. But this is not possible anymore, because obviously here this u times u prime is not anymore, we cannot anymore move this sigma square outside because it's different for each point in time. So we have here on the main diagonal is sigma square 1, sigma square 2, sigma square 3, and so on until we end up here with sigma square at time capital T. We have seen that the covariance is obviously 0, so we have here above and below the main diagonal, like we had earlier, zeros. So that was not the problem. The problem was that on the main diagonal, we have elements here on the main diagonal, and we cannot move the element sigma squared outside because it's different for each point in time. So what follows is we cannot do these operations anymore. So the covariance matrix of our point estimator is not anymore this expression here. So we have to operate with this whole term here. We cannot simplify it anymore by that. That is the problem. So now we have to estimate. The next step is, okay, we have to come up with an estimate. What's that guy? So how can we estimate this term here, this u times u prime. Yeah, what is it? So if we study the literature, we will encounter something that is called the so-called white correction. Yeah? The white correction. And this is a paper published in the econometric literature from White, yeah, 1980. It's more than 40 years old paper. So White suggested an estimate how we can basically compute this guy here. Yeah? So what he suggested was that we know we can run our OLS model and we get our estimated residual vector. Yeah? U1 hat, U2 hat, U3 hat, and so on until U hat capital T. Yeah? So what we do is simply, yeah, we take each element from that vector, square it, and put it on the main diagonal here of the identity matrix. Yeah? So our term u times u prime would be then simply u hat 1 squared on the second element on the main diagonal would be obviously then the second guy from our residual vector u2 hat squared, yeah, u2 hat squared, u3 hat squared would be the third element on the main diagonal until we end up with u capital T hat squared. And above and below the main diagonal are zeros. Yeah, so that's a T by T matrix, of course. Yeah, we know already that our U times U prime or U transpose, that's a T by T matrix. Yeah? But we cannot simplify it anymore now, given that we have this conditional heteroscedasticity going on. So we have to come up with an estimate, yeah, for our product U times U transposed, and this is according to White. We can use this guy here, yeah, this matrix, this T by T matrix. Yeah? So again, how do we proceed in this case? So we have our data vectors, we have our our y vector, we have our x matrix, that's given. So what we do is simply, so we run our OLS estimation. We know our OLS estimator is unbiased. This is an important result. Remember that. So we estimate our OLS estimator, x prime x inverted, x prime y. Yeah. So we use this point estimator and get the residual vector u hat, yeah, that we need here. So and how is that defined? So we subtract from our y vector. Yeah. We have to subtract its y minus x times beta hat, and that's our u hat. Yeah. This is what we get out then. So then we have, once we have our estimated residual vector, yeah, we just we grab each increment, yeah, square it, and put it on the main diagonal of an identity matrix, yeah, and put it into this formula here, and what we get is the covariance matrix of our beta hat. Given we have this covariance matrix, yeah, then obviously we can again run our hypothesis tests using this covariance matrix here instead. And of course, this covariance matrix here that we get out, it must be obviously a k by k matrix, yeah? like it was earlier. So this is how it works out. So just for discussion, so what's the problem here? So the problem is obviously not the innovation process. So the innovation process that basically gives us the randomness, it was based upon the normal distribution. It was a normal distribution with zero mean and variance of 1. So even though we had this random component that was normally distributed, the UT, this guy here, it was not anymore identical distributed. Yeah? We have seen this arch process, it generated a dependency structure in the conditional variance. Yeah? So that was the problem. So, and there are many different arched models or gauge models. Yeah, you might have heard about gauge models, yeah, which basically generalizes the arch models. Yeah, gauge model is a generalized autoregressive conditional heteroscedasticity models. Yeah, so there are many different model variations. So, and the white correction is based upon asymptotic theory. Yeah. And theoretically, obviously, it could be used for any kind of volatility structure, irrespective if we have an Arch1, Arch2, Arch3 process, or whatever volatility structure we have in the data. Yeah. But the question arises, so how well does asymptotic theory that relies on the law of large numbers, how well does it work in real life? Yeah. So what we know is that the beta hat estimator, our beta hat estimator, that's unbiased. Yeah? That was not the problem. So the problem was that we have, obviously, that we cannot simplify this expression here anymore once we have conditional heteroscedasticity in the data. Yeah? So that was the problem. So again, so in this, if we have this kind of dependency structure, yeah, in the residual variance, if we have this volatility clustering, obviously our point estimator is not the problem. The problem is that we have that the covariance is now given by this expression here. So we cannot simplify it anymore. So we cannot use the standard T statistics anymore. They are not valid. Yeah? So we have to take into account that, and we have to operate with a different setup here in order to compound the actual covariance matrix of our beta hat. So, and what we do not know yet is, okay, how well, even though this is theoretically derived, and the thing is, we do not know how well is this covariance matrix estimator in real life. Yeah, so because in real life data can be very different. So, and what we would like to discuss next is a third kind of dependency structure that we might see in the data. Let us now assume, again, we have the same model here, yeah, and we plot our estimated residual process, and it looks now like that. Again, we have here on the x-axis the time dimension, on the y-axis the estimated residual ut hat, yeah, and we have here this kind of pattern. Yeah. It moves around somewhat erratic, yeah, around a zero mean. Yeah. So again, let us assume that we have a random component in innovation process, which is denoted again as epsilon t. Epsilon t follows in identically and independently distributed process that is assumed to be normal with a mean 0 and a variance of 1. Let us assume now that the error process, yeah, of our regression model, yeah, follows this kind of structure, yeah, in an autoregressive process. Yeah, ut is dependent, or is equal with rho, the Greek rho, times ut minus 1 plus this normally distributed error term epsilon t. Yeah? So this kind of process, yeah, which is an autoregressive process of order 1, gives us, or is one potential candidate that might give us a residual process that looks like that. Yeah? And again, this is just one example. Obviously, there are many different other processes as well that might fit, but we will come back to that soon. So let's assume this is the process that generates the residual errors here, and the question is now first, yeah, what's the expectation of that error term? Yeah, we know the errors, in order for our Ols estimator to be unbiased, the errors should be on expectation 0. So that's important to investigate as the first step. What's the expectation of our ut Well, we can just write it down. So if we know that our ut is given by rho times ut minus 1 plus epsilon t, we know also that ut minus 1 is equal with rho times ut minus 2 plus e epsilon t minus 1. Yeah, very simple. So what we can do now is we can use this equation and plug in for ut minus 1 what it is. This is what happens here in the next step here. Yeah, what follows is that ut is equal with rho, yeah, what we have here, times what is here, times rho times ut minus 2 plus epsilon t minus 1, yeah, in parentheses, plus epsilon t. Yeah, what we have here. So we can multiply this out. So obviously this becomes then rho squared times ut minus 2 plus rho times the second term here, which is epsilon t minus 1, and the epsilon term. Yeah? What happens then is now we can do it iteratively. Yeah, we can iteratively plug in for the lagged ut, yeah, what it is. Yeah? So, and we can multiply it out. So, and if we do this many times, what we will see is that we have to open now a math book, and what we will see is then that this sum, or that this equation can be summarized by an infinite sum, yeah, from j is 0 until infinity, from rho to the power of j times epsilon t minus j. So obviously this ut here doesn't matter anymore if we have an infinite sum. So, but it's dependent, obviously, the expectation, or the ut is dependent on an infinite sum of the epsilons here, of lagged errors, yeah, that are multiplied, iteratively multiplied with this rho. Yeah? So this is basically what it means. So what we have to do in order to compound the expectation, we are interested in the expectation of our ut, because that's obviously the relevant error term here. So what's the expectation of our ut? Well, we have to take the expectation of this infinite sum. And again, we know that the expectation operator is a linear operator, so we can move the sum sign outside of the expectation operator. So what remains is the sum, yeah, an infinite sum, obviously, of these lagged epsilon t's. Yeah? And we know that every epsilon t, yeah, has an expectation of 0. So what comes here, the expectation of that guy here is 0. Yeah? So the sum of something that's 0 is 0, which means that the expectation of our ut is 0. Again, what does it mean? It means that our Ols point estimator, our x transpose x inverted x transpose y, is unbiased, which is good news. But what about the variance? So let's have a look at the variance of our ut, given we have that process. So our variance of ut is defined as the expectation of ut minus the expectation from ut squared. We know already from our previous analysis that the expectation of our ut is 0. So what remains is we have to square the ut. Yeah? So the variance is then defined as the expectation of our ut squared. And we have seen this is an infinite sum, yeah, of rho to the power of j, and j is the sum from, it goes from 0 to infinity, and we have to multiply rho to the power of j times epsilon t minus j. Yeah? And this sum is squared. So that's the definition for our variance for the ut. So obviously we can then, let's take the first 3 increments from that sum. The first couple of increments are given by what we see here in the first parenthesis. It starts obviously if j is 0, yeah, then we have what remains here is epsilon t, yeah, because j is 0, so, and rho to the power of 0 is 1. So if then j is 1, so what we have then here, the second term is then rho times epsilon t minus 1, yeah, plus rho squared times epsilon t minus 2 plus rho to the power of 3 times epsilon t minus 3, and so on and so forth. and we have to multiply that, because it's squared here, we have to multiply it with the same parentheses. So we have the same thing here on the right hand side as well. So we have to multiply this out then, obviously. So we have to multiply the first guy with the first guy, which is then ET squared. So the second guy, ET, times rho epsilon t times rho times epsilon t minus 1. We have it here. Then we have to take the first guy here in the first parenthesis with the third guy in the second parenthesis, and so on. So we have to do it step by step. Once we have done with that, we have to take the second guy here and do the same thing all over again. So it's a very large parenthesis here, a very large expression, and we have just depicted here some increments. So it's a very large parenthesis, very large expression. So again, we have to take the expectation of each element. The expectation operator is a linear operator, so we can move it inside. So what's the expectation of the first term here, of epsilon t squared? So the expectation of our epsilon t squared is the variance, right? It's the variance of our epsilon t. So this guy here, the expectation of this guy, is then the variance of our epsilon. So what's this guy here? What's the expectation of rho times epsilon t minus 1 times epsilon t? So they are uncorrelated, right? So it's a well-behaving process, independently identically distributed. So this guy here is 0. This guy is 0, the expectation from this term. What's the expectation of this term here? Rho to the power of 2, rho squared, times epsilon t minus 2 times epsilon t. That's also 0, right? This guy here is 0 as well. But obviously here, this guy here is again, that's the expectation from rho square times epsilon t minus 1 square is obviously rho square times sigma square epsilon. So that's the expectation. So we can go through the whole term here. So it is a very long sequence, obviously. And now we have to open a math book. So what comes out here is obviously that the variance of ut is the expectation again of this whole term here, what we have here in parentheses. And again, we can take the expectation operator inside the parentheses because it's a linear operator. And what comes out then is that it's sigma square from epsilon. So it's the variance of our epsilon process times an infinite sum, again, from j is 0 to infinity, from rho to the power of 2 times j. And rho, or the sum from j, is 0, equal to 0 from 0 to infinity, from rho 2 times j is equal with 1 over 1 minus rho squared. So this expression here is, we can summarize it if we open a math book, it's 1 over 1 minus rho squared. So that means that the variance of our ut is then given by sigma squared epsilon, which we have here. Now we can just put this here to the nominator, right? So it's then given, so the variance of our ut is then defined as sigma squared. So the sigma squared from the variance from our epsilon divided by 1 minus rho squared. And this guy, which means that the variance of our ut is larger or equal to the variance from our epsilon, right? So if the process here, if the rho is 0.5, yeah, this means 1 minus 0.5 squared is 0.25, yeah. So it's this guy here divided by 0.75. So it's obviously so we see that this guy here, yeah, as if rho is unequal to 0, yeah, if rho is 0, then we have the same. Then the obviously our the variance of our ut is the same like the variance of our process epsilon. Yeah, but given that rho is unequal to 0, yeah, if it's 0.5 for instance, or 0.6, 0.7, whatever, then the variance of our ut is larger than the variance of our epsilon process. But it doesn't matter because obviously this guy here is constant. Yeah, that's constant. That's our sigma square, yeah, from u. So we have seen obviously that the expectation, yeah, of our ut is 0, and we have shown here, we have proven that the variance of our ut is constant. So obviously the expectation of our error term is not the problem here, given we have this kind of autoregressive process, and the variance is not a problem either, because it's like our assumption require, our Ols assumption, because we have a constant variance of our ut. But what about the covariance then? Now let's have a look at the covariance of that process. So the covariance from ut and ut minus 1 is given by the expectation of ut minus the expectation of ut times ut minus 1 minus the expectation of ut minus 1. So we know already from our previous analysis that the expectation of ut, respectively the expectation of ut minus 1, is 0. So this expression here simplifies then to the expectation of ut times ut minus 1. So now we can plug in for ut what it is, and what is it? It's rho times ut minus 1 plus epsilon t. Yeah? So what remains is the expectation of, in parentheses, rho times ut minus 1 plus epsilon t times ut minus 1. So what's that? So we can multiply it out. So we can multiply the first term here in these parentheses with ut minus 1, and then we take the second guy and multiply it with ut minus 1. This is what happens here. So we have the expectation of rho times ut minus 1 squared plus ut minus 1 plus epsilon. So two terms. So what's that? So we can, again, that's the linear operator, so we can move it inside the parentheses, and rho is it's a number, it's a parameter. We can move this constant parameter outside the parentheses. So what remains is rho times the expectation of ut minus 1 squared plus the expectation of ut minus 1 times epsilon t. Now, epsilon t is an IID process, normally distributed, so that's the correlation between ut minus 1 and epsilon t, and that's 0. So what remains is the second guy, it's the first term here, which is rho times the expectation of ut minus 1 squared. So what's that? So we know already from our previous analysis, when we were investigating the variance, that the expectation of ut minus 1 squared, that's the variance, that's our sigma u squared. Yeah? And we remember now what it looked like. So it had these sigma epsilon squared in the numerator, and in the denominator was 1 minus rho squared, right? So that's the covariance, yeah, between ut and ut minus 1. Yeah? And that's unequal to 0. And in a similar manner, one can show that the covariance between ut and ut minus tau, what is it? Well, it's sigma it's rho square times sigma square. Or it's actually rho to the power of tau, right? It's rho to the power of tau times sigma square u. Yeah, it's sigma u squared. And that's also unequal to 0. So what does that mean? What are the implications for our covariance matrix of our point estimator beta hat? So obviously, according to our assumptions, the covariance should be 0, right? So let's have a look what's the impact here. Yeah. So like in the previous case, yeah, we cannot anymore simplify our covariance, yeah, matrix of our point estimator. So this guy here is not anymore sigma square the identity matrix. Yeah? So again, we cannot estimate the covariance matrix of our point estimator beta hat by simply sigma square times x transpose x inverted. Yeah? It does not work out. So we have to proxy. So we have to find a different expression for our u times u prime. Yeah? So this does not work anymore. We cannot operate with that standard covariance matrix, which means in turn that our standard t statistics, we cannot use them anymore. So, and now we can have a look at what the literature suggests how we can deal with this issue. So if we open a math book or an econometrics book, so what we'll see is that the literature suggests to estimate this u times u transposed. So, and let's define this u times u transposed. It's not anymore the identity matrix as we said. Yeah? This is not anymore sigma squared the identity matrix, but it's now sigma squared in matrix omega. So how is omega defined? So if we open the math book, and what we'll see is that the omega can be defined like this huge matrix here. So on the main diagonal of this omega matrix, we have ones, yeah, and we have above and below the main diagonal, obviously, the correlations, the autocorrelations. So, and that's obviously clear because we have seen from our derivation that the covariances are the problems. Yeah? Not what is on the main diagonal, but what is above and below the main diagonal. And above and below the main diagonal, we have the covariances. Yeah? So this is the problem, and we have seen how to calculate the covariances between these for the errors, and hence our omega looks like this matrix here. Yeah? So we have our rho here, and it's squared, and it increases in the power, obviously. So if we go here in the first row, yeah, so we see that we start with rho, then the next element is rho squared, then we have rho to the power of 3, and it ends up, the last element in the first row is then rho to the power of t, capital T minus 1. Yeah, so this is a matrix. We can easily code it in a program as well. Yeah, so now we know what is omega. How is omega defined? So how is our sigma square defined? Well, our sigma square is defined in this equation here. It's our estimated residual vector from OLS regression. U hat transposed times omega inverted, the inverse of that matrix, times our residual vector again, and divided by t minus k. When k is again, it's obviously 4 in our case because we have 4 parameters to estimate. Yeah, how is our omega inverted defined? Again, we have to open the math book, and what we will see is this expression here. Yeah, so the inverse of omega, minus 1 is defined as 1 over 1 minus rho squared times this matrix here. Yeah? So this whole expression here is the inverse of that guy. Yeah? We can easily do it with a program. Yeah? So it looks more complicated than it is. Yeah? So we see what's going on here. So in the first row, yeah, it starts with 1, then minus row, and then only zeros follow. Yeah? In the second row, it starts with minus row, then the second element in the second row is 1 plus row squared, then the third element is minus row, then the fourth element is 0, and all the other elements are 0 as well. Yeah, and then the third row, it starts with 0, then the second element is the same like the first element in the previous row. Yeah, so everything repeats basically. Yeah? So it's the main diagonal and the elements, the first element before and after basically, they are always the same here. So this is how it looks like. Yeah, we can easily implement it via a matrix program that we will later use. Yeah, when we implement this in MATLAB, this is actually not a problem. So it looks more complicated than it actually is. So the question arises: how do we get the row, right? And we know already how we get the U hat. Yeah, we get it simply by our Ols estimation. Yeah, so we use our beta hat. We know that it's x transpose x inverted times x transpose y. It's an unbiased estimate. We know that already. So and our U hat is then simply defined as our y vector minus x times beta hat. Yeah, so that's how we get our U hat. But what about the row? Let's have a look at that as well. How do we get this? So what we know is when we do our OLS regression and we include an intercept term, we know that the regression residuals always are 0 on average, right? So what we do is we regress our residual vector. Yeah? Let's denote it here. We have here the first element U1, U2, U hat 3 until U hat capital T. So what we do is we regress our estimated residuals, yeah, on the estimated residuals at time t minus 1. And of course, because it's a regression equation, we have also an error term here, which is assumed to be distributed as normal with 0 mean, yeah, and sigma square E. Yeah, that's the assumption, and that's our OLS regression model. We can neglect now a constant term here because we know that this guy is already summed up to 0. Because this guy is summed up to 0, we do not need necessarily to account for intercept term here. So what we do in practice then is, so we start with the second observation here. Yeah? So we take as our independent variable this our residual vector, but we skip the first observation. Yeah? And we have our vector of let's call it U hat minus 1, yeah? And what's in that vector? So we start then with the previous observation, with the first observation here, right? So it's U hat 1, then U hat 2, because U hat 2 is the observation that is before U hat 3. Yeah? So here you see again it's lagged. So we have as regressor the lagged variables from the left-hand side. Yeah? So obviously the lag from U hat 3 is U hat 2. The lag from U hat 2 is U hat 1, and so on. So that's why we neglect the first observation. So this becomes then a t minus 1 by 1 vector, and the same is here. So we end up here with U hat t minus 1 as our last observation, and that's also the same dimension. It's a t minus 1 by 1 vector. Yeah? So very simple, obviously. So we so we regress obviously this guy here on that guy. That's basically our regression equation. So it's then our rho hat is then given by this guy here, u hat minus 1 transposed u hat minus 1 inverted times u hat minus 1 transposed u. And now remember that our u here that we use for this regression here has one observation less. So that's how we get the estimate for our rho. So once we have this estimate, we can come up with the corresponding. We can construct the matrix omega and omega and the inverse of omega to the power of minus 1, and we can basically implement our covariance matrix of our point estimator beta hat. So that's basically how you would proceed in empirical work. And then what you will also see is if you read the literature, you will encounter the Newey West covariance estimator. So there's a paper also related to the econometric literature, written from Newey West from 1987, who suggests the so-called Newey West covariance matrix estimator. So this covariance matrix estimator can account for autocorrelation structure that we have discussed here, which is very simple. We have only first order autocorrelation, but this guy here suggests a covariance matrix estimator where you can also account for higher order autocorrelations. So this is often used, this is what you will often see in the literature. So now let's have a short discussion, and let's take this away here. So we have seen that we have encountered cases that are obviously frequently observed when we operate in empirical research, and we have seen what are the consequences. So the consequences are obviously that we cannot use our standard t statistics. Our standard t statistics, they are not valid anymore. So we have to come up with adjustments in order to come up with an estimate for the covariance matrix of our point estimator. So we have seen 3 different cases. So the thing is, we can also have combinations, so we can see volatility clustering as well as autocorrelation structure in the residuals. So and moreover, the third case that we just discussed, this can often take place if we take the first differences. So let's say we have variables that seem to be a random walk. So we take differences, and what we can then observe is often that we see volatility clustering and autocorrelation structure. So we have to deal with that somehow. Now it's also important to know that the innovation process that we used for our examples, all the innovation processes, they were normally distributed. So, and obviously we had some models that generated a dependency structure in the regression residuals. So we have seen that they lead to dependency structures in the variance. We have seen when we have volatility clustering going on, that the variance becomes conditional. So there's a dependency structure in the variance, and we have seen in the last case when we were discussing autocorrelation, we have seen that this leads to a dependency structure in the covariances, right? So we have discussed the autocorrelation structure. It's called an RR1 model. RR1. autoregressive of order 1. So we have considered a case where our residual, from our regression model has this type of form. Yeah, it's dependent only on the past, on the past error, and then again we have here epsilon t. So that's an RR1 model, but in real life it could also be that we have an RR2 model, so which means that we have here rho 1 ut minus 1 plus rho 2 times ut minus 2 plus epsilon. Yeah, that's an RR2 model. RR2 model. So it could also be that we have an RR3 model. We don't know that. Yeah, so there are many different candidates possible that allow for dependency structures here, obviously. There's also another model class which we call the ARMA models. Yeah, it could also be that ARMA means autoregressive moving average. It could also be that this ut is a function of its own past, of rho times ut minus 1 plus this epsilon t, which is assumed to be normally distributed with zero mean and variance sigma epsilon square plus theta times epsilon t minus 1. That's an ARMA process. That's an ARMA process 1-1. Yeah, ARMA 1-1. Yeah, so we have one leg of the ut residual, and we have one leg of the epsilon t residual. So, and we can also here we can have many different combinations. So obviously there are many different dependency structures possible in real life. So actually we don't know which kind of dependency structure we are dealing with. So if we have a sample, it could be purely by chance that our model says it's an RR1 process. Yeah, it can be sample specific. It could also be that the real process that generates the data is an R2 process, or it could be an ARMA 1-1 process. So this is something that we do not know, and that is obviously a big problem. So moreover, we have been discussing the white correction, and we have been discussing the Newey West covariance matrix estimator. Yeah, this is what people usually do, what people often use in empirical work and applied work. They use this asymptotic asymptotic covariance matrix adjustments. Yeah? But all of them, they are, first of all, derived using asymptotic theory, which relies in turn on the law of large numbers. So the question arises, how well does asymptotic theory actually perform in real life? We don't know that yet. Moreover, we have assumed that the innovation process, is based upon the normal distribution, right? So these epsilon t's that we use to generate the dependency structure in the volatility or the conditional variance, or the dependency structure in the autoregressive part here. Yeah? We have assumed that these were normally distributed. But this doesn't necessarily have to be the case. We don't know that. So it could be, you see, normally distribution looks like this. It's this bell-shaped curve. But it could be that it follows a t-distribution, which looks more like this. Yeah? So, or let's take a different color here. Let's take the red color here. So the t-distribution, as opposed to the normal distribution, we see here, has fatter tails. Let's say the red is a t-distribution with 5 degrees of freedom, and the black line is the normal distribution, standard normal with zero mean and variance is 1. So both distributions have very different properties. Yeah? So for instance, we know that the normal distribution has a kurtosis of 3. The kurtosis is 3. If we have a chi-square if we have a t-distribution with 5 degrees of freedom, it will have a kurtosis of 9. What does that mean? It means that the kurtosis obviously measures how fat the tails are. So we see that the t-distribution with 5 degrees of freedom, yeah, that we have that allows for larger outliers. Yeah? So we have larger outliers, as we also see in real life. Yeah? So the normal distribution cannot generate very, very large outliers. So what does outlier mean? If we have very, very large outliers, yeah, it means that a very few number of observations have a very large impact on the distribution, yeah, on the cumulative distribution. So, and we don't know that. So we don't know if the innovation process, if it actually is normally distributed, or if it's follows some other distribution, like for instance a t-distribution with 5 degrees of freedom or 6 degrees of freedom. So we know that if the t-distribution, if the degrees of freedom go to infinity, it converges towards the normal distribution. Yeah? But in real-life data, we see often that we have distributions, underlying distributions of the data-generating process that account for outliers, many outliers, yeah? Which have a huge impact on the overall, on the cumulative distribution. Yeah? So we have seen that once we deviate from that our UT, yeah, once we deviate from the assumption that there is no there is no dependency going on. So if we see that we have dependency structures going on, we cannot use these simple t-statistics. Yeah? So we cannot operate with this formula sigma square x transposed x. Yeah? So we cannot use that anymore. So we have to implement different t-statistics. So first of all, to summarize, it is not clear how well asymptotical tests like the white correction or the new West covariance estimator, how well they perform actually in real life finite samples. Yeah? And second of all, we do not either know how well these approximations, how well the white correction or the new West covariance matrix estimator, how well do they perform if we deviate from the normal distribution? What happens if the innovations are fat-tailed distribution? So if the innovation process follows, for instance, a t-distribution with 5 degrees of freedom, yeah, where we have very fat tails. So all these are issues that we will discuss next.